Attention, ladies and gentlemen, it's a pleasure to be here with Charles, with Tia, with Foucoulier, with Mariani. Please, on a scale from 0 to 10, how is my audio? Mainly my audio. Okay, excellent. So today I am starting, I hope, a series of sessions that I'm calling Lean Six Sigma for All, okay? So what's the main objective of Lean Six Sigma for All? As you know, I do run a series of white belt certification programs for free across the globe. We have passed the mark of 100,000 people certified for free. And then I was reflecting about sharing additional Lean Six Sigma content. Obviously, this is not a certification program, okay? So with these public sessions, you will not be able to take the certification test. But I'll be picking, relevant topics in the Lean Six Sigma body of knowledge so we can deep dive. Is that clear? Okay. So I know that here I have white belts, I have yellow belts, I have green belts, I have black belts, I have master black belts. So just to make sure, that we are 100% on the same page. So today, by the way, today is the very first session of Lean Six Sigma for All. I used to run in the past something that I called master classes, Lean Six Sigma master class, but I think this is too fancy. I think it suggests that you must, know the topic very much before you join these sessions. So I want to make these more, I would say, more popular, I want to make these accessible. Maybe the best word is accessible. Okay, is that clear? Type here for me if this is clear. If you are a black belt student, just so you know that we do have our mentoring sessions. Mentoring sessions are private sessions that we run once a month. Okay, this is a different conversation. By the way, coincidentally, our next mentoring session is in 2 days from now. Okay, so type BB if you are my black belt student. Yes, January 16th is our then it's a completely different conversation. It's a Zoom session. I want to hear from you. I want to reply to your specific questions. Okay, but I believe even knowing this is a public open session, you guys will enjoy. So today I will be deep diving on the fascinating, extremely relevant topic, regression. Okay, so from 0 to 10, where are you in terms of knowledge of regression? And 0 is, Marcelo, I have no clue, and 10 is, Marcelo, I know what is regression and I regularly apply regression. So where are you? Okay, 55240303108. So just reinforcing that I love to teach considering that everybody is 0. So if you have already some knowledge about regression, please be patient. Okay. Y as a function of X. So I am asking you about the quality of the audio. We can say that the quality of the audio is a Y. It is an output. It is a response variable. Quality of the audio is a function of what? quality of audio is a function of what? Internet quality, internet speed, microphone quality, yes, distance from instructor to the mic. So if I speak here, there is one certain quality. If I speak from here, it's a different game, you know? So, do you understand when I say y as a function of x or x's? Yeah? Do you understand that? Type yes. So we can model phenomena in nature in many different ways. But every time that we are talking about modeling, we are talking about having at least one response variable and at least one factor, input variable. Sorry about that. Okay, so I will be extremely practical. I'm gonna use here Minitab and also Excel. Thank you guys. And also Excel. And my main objective with you is you need at the end of the session to fully understand the concept of regression and to fully understand how does simple regression work. Okay? Because then when we talk about more advanced modeling techniques, you have the foundation. Okay? You have the foundation. So let's go there. And please, no panic with Minitab. If you are not a black belt student, you have no access to Minitab. And that's okay. So just, look here and try to understand what I'm doing in terms of concepts, not in terms of why did Marcelo go to STAT and then, okay? So, I'm using Minitab. I love to use what they call Minitab help. The vast majority of the tools and techniques in Minitab, you can click here in help, and then there is a web page, I hope you can see, where you can find some explanation about the tool or technique, and almost always you will see an example. Yeah, and I love to use these examples to explain or even to practice, Minitab. So let's take a look here. Our case study is a materials engineer at a furniture manufacturing site wants to assess the stiffness of the particle board that the manufacturer uses. The engineer measures the stiffness and the density of a sample of particle board pieces. The engineer uses simple regression to determine whether the density of the particles is associated, interesting, to the stiffness of the board. Okay, if you found, and then when you click here, you see that there is a Minitab file that you can open up. I had my Minitab open before, but that's okay. Not a problem. Okay, and just to keep it simple, I'm gonna delete temperature. But see, we have density and stiffness. Density and stiffness. And you can consider like any other two variables as long as you have an output and an input. And by the way, which one, based on this scenario here, which one is no way, it's here, it's right here. I wanted you guys to take a look in this text, to determine which one is y and which one is x, but then you guys can see it here. So see, I want to know how does stiffness vary according to density. Okay, so how does this variable here vary according to density? So from 0 to 10, how much did you understand that? It's like, how well is the quality of my audio if I change the variable distance? Yeah? Yeah? If I change the variable distance, how does the quality of the audio change? So, is that okay? Yes? Wonderful. 1 second. Okay, so my son was crying, and that I do have a upper specification limit, you know. So when it goes a little bit beyond my upper specification limit, I just like to check if it's all right. Okay, I have a 1 year old, 1 year old, I would say mini soccer player, you know. I have a 1 year old mini adventurer, you know. I have a 1 year old climber. I have a 1 year old mountain climber. That's it. Oh my god. So stiffness and density. So the way I will explain regression for you is in a practical point of view, very simple, and then I'll yes, a mini Spider-Man, and then I'll deep dive on the concepts. Okay, so how can you run a regression with stiffness and density? Stat, regression, fitted line plot, stiffness in Y, and then density in X. Okay, simple like that. Simple like that. If you are a Minitab user, you know that you can either click once, yeah, and then select, or double click, yeah, double click. You can check different types of model: linear, quadratic, and cubic. Okay, today I'm gonna focus on linear model. Yeah. So before going here, what do we have in this fitted line plot? Yeah. What do we have here? For example, do you know how to interpret? Do you know how to interpret this data point here? How do we interpret this data point here? Well, this data point represents, okay, a density around, yeah, we can click here and see the exact value, but I would say around 6 and stiffness around 8. Yeah, so when we click here, 6.4 density and stiffness 8.08. Yeah, so that's the data point. That's the data point. Wonderful. And there is a cool functionality here that is in Minitab that you can brush, you know, your data. So when you click here, and if I select, I can see exactly in which row I can find my data. So I know that it is in row 8. Wonderful. So if I come here, in row 8, I will find 6.4 and 8.08. So from 0 to 10, how much did you understand that? Type here for me. From 0 to 10, how much did you understand that? Type here for me in 1 second, because I have just closed my monitor, so I cannot see you guys' comments. It's not this one here. Yeah. So I missed your reply. So did you understand the explanation of this data point? Type yes or not. Type yes or not. Discrete data. Okay, I see a lot of yeses. I'm trying to find a no, one no, so I can explain in a different way. Yeah, because then, how many data points do I have here? How many data points do I have here? I should have the same number of rows. I have 29 rows. So if I have 29 pair of data points, I should have 29 plotted points here. Do you guys agree? Yes or not? So if I take here, yeah, all these blue dots, I should see 29 blue dots. Okay? Simple like that. Simple like that. And then when I see a straight line, see that I have a straight line. I do have a straight line. Yeah. What am I trying to do when I plot a straight line? I am already trying to explain how does stiffness behave according to density. Meaning, if I know density, I may be able to predict stiffness. Whoa, if I may be able to predict stiffness, I may be able to plan accordingly in terms of customer expectations. Are you guys following me? Predictability is gold. Predictability is gold. From 0 to 10, how much did you understand that? If you are able to, if I leave my water 3 minutes, 4 minutes, 5 minutes, if I use this type of coffee bean, you know, if I prepare in this way, I know I can predict Marcelo's satisfaction as a customer. Do you guys think market in general, you know, corporate companies, manufacturing service, SME, small and medium enterprise, they are interested in tools and techniques that would help them, you know, to predict process performance? Yes or not? Or customer satisfaction. Do you think they value that? Yes, they value a lot, a lot, a lot, a lot, a lot. So there is a very high chance that if you speak this language of regression, regardless the technique, if you speak this language, there is a very high chance that you become more relevant, okay? Wonderful. So, okay, how did I plot this straight line here? So I tried, or the software tried, to plot a straight line where the distance, okay, I would say the vertical distance to each data point to the line is minimized. Okay, so how can I plot a straight line in a way that the vertical distance, okay, between each data point and the closest point in the line is minimized? Okay, if you are a statistician, mathematician, or if you had a chance to study regression before, you know that I'm using the famous least square methodology, okay? And what's the advantage of plotting a straight line in a way that the vertical distances of all data points are minimized? Well, with a straight line, I can easily and quickly find a model, an equation, a mathematical model. So do you guys understand the value of having an equation? For example, if I know density, let's suppose density is 20, you know, I can come here and substitute and put 20 times 3.541, yeah, then I'll have something around 70 minus 21.53, so we would have 40 something, right? So when I have a density of 20, according to the formula, according to the model, according to the equation, I will have something around 40. Do you guys understand that? Yes? I have an equation, I have a transfer function, I have a model. So when I have x, I can predict, yeah? I can predict, yeah, y. And then I can predict perfectly, right? I can predict very accurately. Is that right? So for example, let's use an Excel here. Let's use an Excel here. So I can predict y knowing x, yeah? I can predict y knowing x. So for example, if x is 20, yeah, or let me do x and y. If x is 20, I can predict y. How? There is a formula. There's a formula, minus 21.53 plus, yeah, 3.541 times this guy here, yeah, so 49.29. Now something very interesting. If I place, you know, x in 20, yeah, I will have, can you guys see here, if I place in 20, almost 20, I'll have 49.25. Yeah? 49.25, pretty close, very close, very close, very close. But I have a question. I have one data point here. Take a look. Where the density is 23.3. Okay, 23.3. So according to my model, to my equation, if x is 23.3, the y would be 61. Okay, so if x is 23.3, y would be 61. Whoa. 61 to 49.51, it's a huge difference. So type error if you understand that there's an error in my equation. It's like an inconsistency. It's an inconsistency. I was able to build a model, an equation, but when I check this model with reality, I just found, I would say, a major inconsistency. Because using this equation, when I say density 23.3, you know, the equation says 60 something, says 61, but reality is pretty different. Reality is 49.51. So what's going on here? What's going on here? So there is a very famous quote from Professor George Box, okay? Professor George Box, one of the most important people, if you like stats, or if you like stats applied to continuous improvement, George Box is definitely one of the people that you wanna research about, okay? And then George Box model, there is a famous quote. Take a look. All models are wrong. Some are useful. That's a good one, right? That's a good one. So this kind of error, let's say, this kind of inconsistency, this kind of misrepresentation of reality will happen always at different levels, but all models will present a certain level of error. All models will be by nature, they will be wrong. Are you guys following me? Type yes if you are following me. And then what do? Well, we need to know if the model is good enough for us to make practical decisions that are assertive. We want to be assertive. Yeah? So depending on the scenario, if I am predicting that it is 60 and reality is 50, depending on the context, it is okay. It's okay. It is okay. By the way, in a regression analysis, you can even include something that we call confidence interval. Okay? So when you include a confidence interval, it's like you are saying that if you take, for example, 30, 100, pieces, and with this level of density, with this value of density, the mean in terms of stiffness, would fall in this interval. Yeah, would fall in this interval. Yeah. Just to simplify. And you can also include, if you don't want to talk about mean, you can include what we call prediction interval. Yeah, normally it is wider. So prediction interval, it has to do with margin of error per data point, an individual data point. Now I'm not talking about 100 parts, with this value of density. I'm talking about one single data point, So if I take one single part, I would expect, for example, for density 25, I would expect to be in this interval. Yeah. Wonderful. Excellent. So if you've learned something new so far, type here for me, Marcelo, I've learned something new. At least one thing that made, this time here spent worthy. And then, wonderful, excellent. Now, I want to deep dive, or before that, let me see if you guys have any questions. Take a look here and let me know if you guys have any questions. All questions are welcomed, okay? Type here for me if you have any questions. And if you have no questions, type here for me. Let's move on. Let's move on. Wonderful. So now I'll go a little bit more technical, but I'll go very slow, and I hope you guys can follow me, okay? Wonderful. So I believe the equation, you are pretty good, yeah? So maybe just an interesting thing is this constant here is pretty much the stiffness when density is 0. And obviously that many times it doesn't make any practical sense, okay? But mathematically speaking, if I change here the x to, let's say, minus 5, and if I change here to minus 50, yeah, and if I just come here and I keep, plotting here the straight line, yeah, is that correct? I am just terrible drawing because it would be, yeah, let me just change to 0 here, 1 second. 0, yeah, so let me see if this is easier to observe, yeah. So take a look. I hope this is good enough. When density is 0, if I put 0 here, 0 multiplied by 3.5, it is 0. And then I'll have only minus 21.53. Yes, that is exactly this point here. Exactly this point. Okay, just out of curiosity. And that 3.541 is really how much the stiffness will go up per unity of density. So when density moves from 1 to 2, stiffness will move 3.541 in the Y scale. 3.541 per unit of density. Okay? So one way of seeing this is if you pick, for example, let me put here 0, 1, 2, 3, 4. I'm putting more ticks here, and then I'll keep doing that. Let me take a region here, 10, 11, 12, 13, 14, 15. Yeah. So if I take here, for example, from 12, the stiffness is 20.6. Yeah, 20.6. If I take 13, it is 24.6, you know, or 24 point a little bit above, you know. So see that I moved just one unit for X as 20.88. 12 and 13 is 24.6, you know. So again, we are moving 3.541 in the Y scale per unit of X. Okay. But one important thing for you to know is definitely the standard deviation of the model, but mainly R squared and R squared adjusted. Okay, very much important, okay. As a Lean Six Sigma professional, I would say it is mandatory that you fully understand R squared. So now I need to use a special technique. Attention, ladies and gentlemen, pay attention. You have not discussed what do you do when the model is wrong. You are not paying attention. With love. You are not paying attention. All models are wrong. Pay attention. All models are wrong. Some are useful. So what? Yes, but some are useful. So what to do when the model is wrong? Die? Maybe we should abandon this life, you know, because all models will be wrong. Cry. What should we do when our model is wrong? Let's cry. When the model is wrong, let's play a sad song. Oh, yeah, when the models are wrong, we play. So let's play a sad song every day. Guys, once again, I'm just trying to reinforce an important concept. Okay, all models are wrong. Some are useful. So what do I mean by that? For some models, you will be able to extract some important practical conclusions, okay? With love, with love, with love. With love, with love, with love. Nemequite Paia, Aline, tudo bem? Yes, with love. Type love if you understand that I'm saying this with love, okay? Because this is very important, very important. When you're using the mini-table regression function, it will populate the red line on the table. When you go in this option, Fukuili, that is fitted line plot, when you go stat regression, then you don't have the scatter plot, okay? Yes, with love, with love. But now I wanna explain what is r squared and why r squared. R, the letter R, power 2. R comes really... Because see, there is an ANOVA running behind here our regression, okay? And the ANOVA is Peter Fisher. Ronald Fisher is the man, or was the man. Ronald Fisher is considered the successor of Charles Darwin. Okay? Ronald Fisher is the man. If you have time, please research about Ronald Fisher. He's the father of ANOVA. Yeah? But the creator of this concept of R that is connected to correlation analysis is a guy from the same country that started his career a little bit earlier. Carl Pearson, very famous too. Yeah? And you should be careful in debating which work is more relevant. Yeah, because there are some records that suggest that Pearson was almost chasing, Fisher in order to find inconsistencies in his work, because again, Fisher was much younger than Pearson, or younger than Pearson, and at some point the work from Fisher was clearly more popular, maybe more relevant. I find way more relevant. And then there's, just out of curiosity, there are some records that suggest that Pearson was not so happy with that. Yeah. We never know how much truth is in it, but we hear this quite a lot. Yeah. But the fact is, many things that we use in continuous improvement in terms of stats, they come from Fisher, from Ronald Fisher. So it's an important guy, no doubt. So one way of understanding R squared is just getting, you run a correlation analysis with the same data, you take the Pearson's correlation coefficient and just square, power 2, just that, But another way of finding R squared, and I'll show here, is using ANOVA, yeah, more specifically the sum of squares. But before that, what is the right interpretation of R squared? So how should I read this number? How should I read 84.47%? So in my point of view, the best way to read this is, I can see that Y is varying. I can see that the Y is varying, stiffness is varying. Sometimes the stiffness is 14.81, sometimes it's 7.57, sometimes it's 5.3, sometimes it's 43.24, sometimes it's 28. So do you agree that Y varies? Y varies. I want to understand why is Y varying? How can I explain that? Well, R squared is saying that you can explain 84.47% of the variation in Y with this model. Whoa. And in this case with density. So you can say that density explains 84.47% of the variation in Y. The variation in density explains 84.47% of the variation in stiffness, or 84.47% of stiffness variation can be explained by the variation in density. Type understood if you understood that. Okay? Hello, Eduardo. So see, I can easily see that Y varies. Sometimes it's 7.57, sometimes it's 19.44, sometimes it's 43, So how do I explain? How can I explain? Sometimes I am happy with my coffee. I have an example here, but I am afraid that type OK if I can share a risky example. Type you're okay if we can manage this risk together. and I will say this with love. Okay? It may be risky. I am married to the police chief's daughter of my city. She's an attorney, she's a lawyer. Is it fair, type fair, if it is fair to say that all of us, we have variations in our humor? Sometimes we are in a good mood, bad mood, yeah? My wife is the same. Sometimes she's very irritated. Sometimes she's the sweetest person in the world, yeah? So there is some variation. I swear to God, I found out a model. It's wrong. It is wrong. But I think it's very useful. I found out a variable that explains the variation of humor in my wife. That is food. Simple like this. If she's hungry, yes, if she's hungry, the chances are much higher that she's annoyed, she's irritated, she's pissed. Are you guys following me? So now apparently I know how to explain her humor variation. I know how to explain that amount of food in her stomach. So what's the value? I see someone here that just asked, what's the value of regression? Probably you have just joined the session. Yeah, because if by now you are asking what's the value of modeling processes, I think you are in the wrong life. Not wrong life. Okay, wrong life is maybe. But if now you are asking what's the value of regression, I mean, there is something wrong with you, my friend. Very much wrong, So if you can model your process, you can predict performance. And if I can predict when my wife is getting irritated, I can act upfront. I can proactively plan. I can plan accordingly and guarantee that she will not be hungry. From 0 to 10, how much sense does it make? So if I have a model, even knowing that the model is not completely right, it is very useful, very useful, very useful. And we can apply this in manufacturing, in service. If I know that the diameter of the multi-wired copper cable is a function of the composition of the synthetic diamond in the last step of extrusion, I need to control that. Because if I control the composition of the synthetic diamond, the last step of the extrusion process, let me control this, because then I will not have, I am acting, I'm being proactive. Yeah, we like that. No, this is an open session. This is for everyone. Okay, this is for everyone. Yeah. Yeah. I specialize in digital marketing. I'm comparing this to density is the ad spent and the stiffness is the oh, beautiful. So see, I just want to check if I'm understanding this correct. I am specialized in digital marketing. I'm comparing density with ad spent or expenses and stiffness with conversion rate. Yeah, because see, the percentage of your audience of unique viewers, that are buying your product, for example, you need to check if this is a function of how much are you spending per day. But there are even better examples in your scenario, because conversion rate may be a function of the ad that you are using, the creative, the copy, the text that you are using. It is also a function of geography. So I know nowadays, I know exactly the countries where people are they are interested, but the conversion rate is low. For me, I have a map of the entire world. I know the countries where I'm gonna spend more with ads, but the conversion rate is so high that it is okay. There is an ROI or ROAS, as we say, return on advertisement services. But you are thinking correctly. You are thinking correctly. It's like stock market. Yes, the problem with stock market is the number of variables is just insane, Ed. So as you probably know, it is one of the hardest places to model, the number of variables is just insane. The value is piece in this case. Exactly. Yes. Wonderful. So and now, guys, I will go a little bit more technical. Type technical if you are okay. If I go a little bit more technical here, R squared can be calculated by, this is an ANOVA table, okay? ANOVA table. I have degrees of freedom, sum of squares, mean squares, F and P value. Okay, so sum of squares, if you take here, for example, the amount of variation associated to the regression, error, and total, you will see that if I take here r squared, okay, one of the ways to understand that is simply taking 11,552.8 divided by 13,676.7. 13,676.7. Okay, so see 84.47%. And again, this is, it may be a little bit too technical, you know, but just at this point, out of curiosity, how can you calculate that? And what's the main difference between sum of squares and mean squares? You are pretty much dividing sum of squares by degrees of freedom. And what's the concept of degrees of freedom? It's really how much room do you have to explain something with the amount of data that you have. Okay, another very simple way to understand that, for example, Aline. Let's suppose Aline, she has 5 houses. Okay, she has 5 houses. So she has one in Orlando, Paris, Dubai, Itajubá, and São Paulo. Let's suppose she is in Orlando, but then she gets like bored, you know, tired of Orlando. How many possibilities does Aline have of going to another place, you know? So knowing that she has 5 houses, if she is right now in one of her 5 houses, she has 4 other opportunities. Okay, that's why degrees of freedom almost always you see n minus 1. You know, if she's in Paris, she can go to Orlando, Dubai, São Paulo, or Itajubá. She has 4. You know, so see, that's why we have here in total 28. That is really 29 data points, 29 or rows minus 1. Yeah. Regression, normally we take the number of it's the constant plus the terms. Yeah, so we could say that here we have two elements, 2 minus 1, we have 1. And then mean squared is nothing but sum of squares divided by degrees of freedom. So this guy here is nothing but this guy divided by 1. This guy here, 78.7, you can do the math. It's nothing but 2124 divided by 27. And if you want, you can plot here this guy divided by this. That would be the total for mean squared. Because every time that you are modeling, you have only 2 options. You know, it's model, I mean, you are fully explaining, you are fully right and or fully accurate, or error. It's model or error. I'm being assertive or error. Yes, so this ratio is very important. And by the way, this guy here is the famous mean squared error, MSE. And with MSE, if you take the square root of MSE, you have the standard deviation of the model. Yeah, so if you take S is nothing but 78.7 square root. Okay, so see, this is the standard deviation of the model. And the standard deviation of the model, what's the practical, simple explanation? The standard deviation of the model is connected to the precision of your model. And it has to do with something that we call residuals. Residuals, this distance, you know? For example, which model do you think would be more precise. You know, let's put here density, stiffness, stiffness 2. Okay, so let's suppose we have here, let me do something very extreme, you know, or let me just change few numbers here. Let me change this one here on row 21, so let me copy this. Okay, and then in row 21 I'm gonna make this data point here much closer to the line. Okay, so row 21 here, instead of 96 I would say, instead of 96 I would say 68. Okay, so what am I trying to do? 68. Okay, so let me run the regression with just one change here, and let me see if I can reduce the standard deviation. Okay, let's see. Sorry about that. So can you guys see that now I have a second scenario? I have a second scenario where I don't have this crazy data point here. It's much closer. It is much closer to the red line. Do you guys understand that? And everything else remains the same. So see, there is a difference in terms of the standard deviation. The standard deviation of the model, when I don't have this, let's say, just to keep it simple, that crazy data point, maybe an outlier, the standard deviation went down. And when the standard deviation goes down, I am saying that my model is more precise. Do you understand that? Yeah? Wonderful. Guys, today, just to finish like this explanation, today I wanna also talk about the R-squared adjusted that is calculated based on mean squared. Okay, so if you come here, the formula is pretty simple. Maybe one of the easiest way. Yes, I like to calculate this. That is so the mean squared total, you will need that, is nothing but 10,825.3 divided by 28. Okay, divided by 28. So I have this 386. Okay, 386. This is the total and this is the error. So one of the easiest way to calculate R squared adjusted is just take this one here and copy so we can follow. And in case you guys are taking notes of that, it's very simple. Once again, you can easily go to, take a look here, stat regression, fitted line plot. Remember that you have not only examples, okay, not only examples, but if you click click here on these three lines, you see overview, data considerations, example, more statistics, and then you will see here methods and formulas. Okay, so what I was saying about the standard deviation, yeah, that is the square root of mean squared error. You will find the same for r squared, yeah, sum of squares for the factor, in our case the regression, and sum of squares total, and the adjusted, you know, if you want, you can use this formula that is 1 minus mean squared error, and the denominator we have just processed, you know, total. So if you take, well, equal 1 minus 46.8 divided by this guy here, okay, and then obviously this is percentage, okay, 87.90, and obviously you will find some differences here sometimes because of rounding error, okay, rounding error, in this case up to the second decimal place, but if you increase here, if you go to 16 decimal places, for example, yeah, and you open up here, you start seeing some differences, in this case in the fourth decimal place, okay, in the fourth decimal place. And what's the interpretation of mean squared adjusted? There is a problem with r squared, yeah, r squared and r squared adjusted, with r squared, because when you start adding terms to your model, r squared will always go up. I'll say that again. The larger the number of terms in your model, the higher the r squared. This is good and bad. This is dangerous in a sense that when you add more terms to your model, I mean, we are talking about, because remember that each coefficient, for example, is associated to an error. So the more terms you have in your model, obviously, naturally, the higher the risk. The larger the number of terms, the higher the risk. In simple words, yeah? So everyone that works with modeling, we love to optimize the size of the model as much as possible. And then every time that for the same data set, you need to find the best model with the optimal number of terms, you will be using r squared adjusted. Why? Because r squared adjusted considers the value, yeah, the amount of explanation that comes with each term of the model. So if you add a model that is costing, you know, something that is not proportional to the value that it is bringing in terms of sum of squares, r squared adjusted will feel that, so it will go down. R squared will always go up if you include more terms. R squared adjusted, no. So whenever you have many different models with the same data set and you are deciding the best model, you use r squared adjusted, and then you just pick the one that has the highest r squared adjusted, unless you have like a model with 20 terms, r squared adjusted 90%, and then you have another model with just one term or two terms that is 89.9, you know, very close, but the model is much reduced. Then you you may decide to pick this one, even knowing that it's not the highest R-squared adjusted. Okay, ladies and gentlemen, this is regression analysis. Type helpful if you found this session helpful. Let me see if I can quickly, answer. Can you have a simple explanation of degrees of freedom? Yeah, Aline, the best explanation that I found, because for example, see, here in this case we had 29 rows, and by the way, for regression we recommend at least 40. 29, so degrees of freedom is 29 minus 1, 28. Yes, why the number of elements minus 1? Terms of we had 2 terms in our model, then degrees of freedom for the models just 1. Why 2 minus 1? So I think it has to do, because see, we are trying to explain things. When we are trying to explain things, Aline, we move from one place to another. So it's like you going to one, from one data. It's like I am analyzing the first row. How much did I learn here from the first row? Okay, how many more rows do I have? How many more rows do I have to learn something? Well, I am already in the row number 1. So I have, in this case, 28 more rows. Are you following me? 28 more rows. So what does it mean? It's really some people just simplify saying that it has to do with the amount of data that you have, but it is more than the data, because for the regression it's the term of elements, so it's really the amount of information, that you have to perform to investigate, to perform your analysis. And the term degrees of freedom, it's like grau de liberdade. Yeah, how much freedom do I have if I have 5 places to go? Well, probably I am in one of them. So if I want to move, I have 4 other places. Yeah, you got it? Beautiful, beautiful. Professor, is this recorded? Yes, these open sessions will remain here on YouTube. Yes, wonderful. Did you find it helpful? Guys, thank you so very much. Stay blessed. I will do my very best to be here with you guys at least once a week for these open conversations, okay? I hope you find this helpful, and I hope these conversations will make you an even better professional and problem solver, okay? Thank you so very much. Bye-bye.